Hello, welcome to part 1 in a two-part series of the Back to School AP Calculus Review Worksheet. In this, we're going to be covering a few things in the whole video. We're going to be covering log functions, exponential functions. We're going to be covering a lot of trigonometry, and we'll be covering a little bit of rational functions. So in part 1, we're going to be discussing graphing some of these functions and understanding the domain and range of these functions. So first today, we're going to start with the logarithmic function. Your typical graph for logarithmic is going to be based around y equals log of x. And for the purposes of today's video, we're going to make that log base 3 of x just so we can start getting into the key point mindset. So when you're graphing all these things, it's hard to just memorize the graph. What I find is most helpful is to kind of think about where the key points would go and remember the graph from there. So the first main key point for logarithmic functions is 1, 0, and I'm going to show you how we're going to get there. So if we plug in 1 for x, we get y equals log base 3 of 1. Now, anything log 1 is going to equal 0. So that means that y equals 0, and our point becomes 1, 0. So we're just going to graph that, and I'm going to label that 1, 0. Now, the next key point that we're looking at is we have this base of 3. So we are going to plug in 3 for x. Y equals log base 3 of 3, which whenever we have a log of something that's the same as the base, we get 1, because our goal in logarithmic functions is to find what the base needs to be raised to get to the number that we're throwing into the function. So 3 raised to the power of 1 is equal to 3, therefore y is 1, and our function becomes 3, 1. So that's another key point here. So go like there-ish. Can get that to draw, and we'll label it 3, 1. Now, whenever x is less than 1, y is going to be negative, and then it's going to go up, and this does keep going up a little bit, not as steep as exponential functions though. So in terms of talking about domain and range, there are a couple of things to consider. So if x is 0, the function is undefined, and if x is negative, the function is also undefined, which means that x must be greater than 0. And range-wise, we can see that really you can have any range because it goes all the way down and it's just going to keep going up. So the range is going to be reals. So that's logarithmic functions, pretty simple, and we're going to move on to exponential, which is the opposite of these. So now let's discuss the exponential function. So when we're talking about exponentials, the general equation is y equals a times b to the x. For today, we're just going to be looking at y equals 3 to the x, just so that we can discuss some of the key points that we've been looking at. So the first thing that we're going to plug in is we're going to plug in 0 for x, and we're going to see what we get. So y equals 3 to the 0. We know that anything to the 0 power is 1, so y is going to equal 1. So if we plot this, it's going to equal 0, 1. So that's our first key point, 0, 1, and I'll label that at 0, 1. And our next key point is going to be, we're plugging in 1 for x. So y equals 3 to the power of 1, y obviously equals 3, so our point is 1, 3. So I'm also going to plot that, 1, 3. Okay, now when we talk about exponential functions, we know that the exponential function is going to keep curving up, and whenever it gets negative, we know that it approaches 0 as x moves to negative infinity, which means that our graph is going to look like this. Now, speaking domain and range-wise, domain can be anything. You can have anything plugged into an exponential function, but range is x is greater than 0, because there's nothing that can make the function approach 0, or nothing that can make the function equal 0, just approach 0. And if we actually look at the domain and range, we know that's the opposite of a logarithmic function, which makes sense given that a logarithmic function looks a little bit more like this, right? So just the opposite of that, which makes a lot of sense. Now we're going to do a little bit of comparing and contrasting of some different rational functions. So the first rational function that we're going to look at is 1 over x. So when we're thinking about 1 over x, there are a couple different things that you can think about to kind of remember what this function looks like. I like to plug 1 in for x, and obviously 1 over 1 is going to equal 1. So there is a key point here. And if you plug in -1 for x, 1 over -1 is going to be -1. So you get the point -1, -1. Okay, now when you're talking about going from here, I like to think that the bigger x gets, the smaller y gets. Because when you have like 1 over 1,000, right, as x starts to approach that infinity, it gets smaller and smaller, which means that we're going to see a decline in the value of y. And as x gets smaller, so as x becomes like 0.1, then we see a rise in y. And we see the kind of same thing in the negative. As x becomes like -0.1, y starts to get deeper into the negative, so the absolute value number gets larger. And as x starts to get larger into the negative, let's say -1,000, that fraction number gets smaller. So we have like -1 over 1,000, which is very tiny. So this is kind of your graph for this, and I'll label these key points here: 1, 1, and -1, -1. So as you can see, x can never approach 0 because x is on the denominator, which means that in our domain, the only restriction is that x cannot be 0. And in our range, we see that x is approaching 0 from both directions, which means that x is greater than 0 and x is less than 0. So we can see that it's going from -infinity to 0 and then 0 to infinity, non-inclusive. Now let's look at our domain and range of our other function, 1 over x squared. So when we look at 1 over x squared, there's a similar kind of graph here, except for one thing. So when we plug in 1, we get the same thing. 1 over 1 squared is 1. So we get the point here, 1, 1. And I'll label that 1, 1. But when we plug in -1 for x, we actually get +1 because -x squared is 1. So we have this point here instead. And so it's going to see the same curve as I explained earlier. And we're just going to curve that up. So you can see that now the range, instead of being x is greater than 0 and x is less than 0, is just going to be that x is greater than 0. Because you can see it's never in the negative. And the domain is still that x cannot equal 0. So that's pretty simple for rational functions. Now let's talk about the cosine function. So our equation for cosine is y equals cosine of x. And when we're designing our cosine graph, we need to think about the unit circle. So we need to think about where does x hit 1, where does x hit -1, where does x hit 0. So when we're kind of thinking about drawing our graph, we're going to think about a similar method. So we're going to start our graph at 0. And I'm actually going to start it a little further this way. And so we're going to break up our period into 4. So we find our period by doing 2 pi over k, and k is the coefficient of x. So in this case, k is going to equal 1, which means that our period is equal to 2 pi. So now to find the intervals that we're going to go by, we have 4 intervals after this 0 here. We're going to divide the 2 pi by 4. So 2 pi over 4 is going to equal pi over 2. So that's what we're going to go by. We're going to go pi over 2, pi, 3 pi over 2, and 2 pi. And I'm just going to add a bar here. Okay, now, when we're thinking about the unit circle, we know that when it's just cosine x, the height is going to reach 1, and the lowest point is going to be -1. And so we know those are going to be our highest points and lowest points. So now, in terms of actually looking at how to graph this, we need to think about when cosine hits those 1s, -1s, and 0. And then we can kind of graph what's in between. So when cosine is at 0, we know that it hits a point of 1. When cosine reaches pi over 2, it drops to 0. When cosine reaches pi, it goes to -1. When cosine reaches 3 pi over 2, it goes back to 0. and then when it hits 2 pi again, it goes up to 1 again. So just connecting those points, we get this graph. And then if we go on the other side, if we have negative pi over 2, it goes back down to 0, and it kind of continues that way. So in terms of domain, cosine can be all reals. You can plug anything in for cosine. And in terms of range, we see that at the highest point, cosine is going to reach 1, and at the lowest point, it's going to reach negative 1. And those are inclusive, and so that is the range. So that was pretty simple, and now we're going to look at sine. So when we're looking at sine, we're going to look at a pretty similar thing to cosine. We're just simply going to look at y equals sine of x. Now, the points here are a little different because sine reaches different points, different places. But we're going to keep the same kind of general period because 2 pi over 1 is still 2 pi. And so that's going to be the period. So that's how long it takes for the function to return to its original position. So looking at the key points, when sine is at 0, it's going to equal 0. When sine is at pi over 2, it's going to reach a high point of 1. Then when sine goes back to pi, it reaches another point of 0. Then sine is going to dip down to negative 1 at 3 pi over 2, and then come back up to 0 at 2 pi. So this is what the sine graph looks like. And then we can see that at pi over 2, negative pi over 2, it's going to reach a low point of negative 1. And so that's kind of what the graph looks like. You can see it's really just a transformation of the cosine graph. We can see kind of right here where the cosine graph is, and we can see that it's really just shifted over pi over 2. But that means that the domain and range are going to stay the same. So domain is reals, and the range, it still reaches a low point of negative 1 and high point of 1. So that's our range. Now we're going to look at tangent. So looking at the tangent function, there are a couple things that we need to know. So first, y is going to equal tan of x. Now the really difference between tangent function with the other functions are that tangent x is also equal to sine x over cosine x, which means that whenever cosine x is equal to 0, the function is going to be undefined, which means that we have some asymptotes that we didn't see in those other functions. So we know that cosine x is going to equal 0 at pi over 2 and 3 pi over 2, which means that we cannot have the graph here because then it's going to be undefined. So we need to see those asymptotes there. Okay. Now, when we're looking at where to go from here, we know that when sine is 0, the function is going to equal 0, because then cosine is 1 and 0 over 1 is 0. So we're going to put a dot there. And we know that when x is pi, we know that sine pi is 0 and cosine pi is 1. So 0 over 1 is also 0, which means that we have these 2 points here. Now, looking at tan, we know that tan is going to go up this way, because as sine gets closer to 1 and cosine drops and gets into the decimal places, we know that that's going to shoot up sine. So as cosine becomes 0.0001 and sine is getting closer to 1, that means that the number of y, the range, is going to be huge. And we know that when cosine is getting closer to negative 1, right, so when cosine is dropping, or when sine is dropping to negative 1 and cosine is approaching 0 as well, we know that this function is going to shoot down because it's going to be negative. And we can kind of see this graph all the way through. So there you go. So the domain of this, we know, is all reals except for these asymptotes that we have. And we're going to write that as x cannot be equal to pi over 2 plus k pi, which means that any multiple of k, so any integer value for k, so k is an integer, right? And so any value of pi, we know, plus pi over 2 is going to be an asymptote. So, right, we have pi over 2 plus pi is 3 pi over 2, so those are all asymptotes. And the range is going to be all reals here, because we can see that the graph goes all the way up and all the way down. Now, we are going to look at one of these kind of opposite functions. So we're going to look at the secant function. So the equation for that is y equals secant x. And that is also equal to 1 over cosine of x. And the 1 over cosine of x tells us a couple things. So similar to the tangent graph, whenever cosine of x is going to equal 0, that means that our function is going to be undefined, which means that we're going to have asymptotes at those specific places. So for example, when x is equal to pi over 2, cosine x is equal to 0. So we're going to have an asymptote there. And then same with 3 pi over 2. And then same with negative pi over 2. Okay, now if we look at kind of the different places that we are, when cosine of x is equal to 1, we know that when x is equal to 0, then we know that cosine of x is equal to 1, which means that 1 over 1 is 1, and so we have this point here, 0, 1. And when cosine of x is kind of approaching that pi over 2, we know that that 1 is going to drop into a 0, which means that that's going to give us a decimal value, and 1 over a decimal value is going to give us a number greater than 1. So we're never really going to approach down into any of like this area. So then kind of looking at the opposite of that, whenever x is coming to pi, then that's the range of that is going to be negative 1. So cosine of negative 1, or cosine of pi, is negative 1. So 1 over negative 1 is obviously negative 1. And as we go back up and try and approach 0 again, from that negative value, we are going down because 1 over a decimal shoots it down. So that's where we kind of get the secant graph from. So you can see it never goes into the negative 1 to 1 range. So our domain is going to be reals except for these asymptotes, which means that we can say x is not equal to pi over 2 plus k pi. And the range we can say is x is greater than 1 and x is less than negative 1. Actually, let me say less than or equal to. So that's the secant function. And if you want to review the cosecant function, the graph is really just shifted. So it's the same graph as the sine graph, but same graph as the secant graph, but it's shifted over pi over 2, which means that the asymptotes are going to be opposite of this. And that concludes our video. We have one transformation here, so we'll just quickly move on to that. The transformation that we have is y equals negative 2 sine of 3 pi x minus pi over 2 minus 1. So I'm going to rewrite that as y equals negative 2 sine of 3 pi times x minus 1/6 minus 1. So now when we start to look at this period for this, we know that the period is equal to 2 pi over k, and at this point k is going to equal 3 pi, which means this is 2 pi over 3 pi, which equals 2/3. So our period is 2/3, which means that our intervals are going to be 2/3 over 4, which equals 1/6. Now looking at graphing this, we know a couple of things. Actually, let me do this. So we know that we're starting at 1/6 because the graph is shifted right 1/6. And we know that there are going to be intervals of 1/6. So actually I'm going to start the graph right here at 1/6. And I'm going to go up by 1/6. So we go to 1/3, and then 1/2, and then 2/3, and then 5/6. And so that's kind of our full length graph here. And I'm going to make my axis here at 0. Okay, so we know that our amplitude is 2. You can kind of see that here. So our amplitude is 2. And we know that it's reflected over the x-axis. So because that negative is there, we know that's reflected. And we also know that it's shifted down 1, which means that I'm going to start this graph At -1, it's going to be our base point, and I'm going to move it up 2 to get to 1 and down 2 to get to -3. And so it's sine, which means that at our base point is going to equal 0. So I'm going to do this in another color so you can see this. But at 1/6, that means that our graph is going to equal 0. Now at 1/3, normally it would go up to the highest point, but because it's reflected, it's actually going to go down to the lowest point, and then back up to 0 at 1/2, and then now up to the highest point, and back down to 0. So that's what our graph looks like. Kind of when you're looking at these transformations, you really need to think about the period, how you're going to apply your intervals, and how your shifts affect your amplitude and where the graph is starting. So really, they're not that bad. It's kind of similar with cosine transformations, and it's really the same for any transformation that you look at, including logarithmic and exponential. So I know that was kind of a long video, but I think that the domain and range of these functions are super important. So if you sat through this, I'm very glad you did, because I think the domain and range of all these are important things to know. Come back to part 2 to review the actual functions themselves and how to kind of use those functions and solve equations